Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to Lecture 3, Organic Chemistry 3. Today we will continue on amino acids, peptides, and proteins. Synthesis of amino acids. The first method is amination of alpha halo acids. So starting with carboxylic acid, add bromine phosphorus tribromide, then hydrolyze the product. We obtain alpha bromo acid, which upon treatment with excess ammonia leads to the formation of alpha amino acid ammonium salt. Method 2, Strecker synthesis. Starting with aldehyde, treat aldehyde with ammonia, ammonium chloride, sodium cyanide mixture. We get alpha amino nitrile, which upon hydrolysis in acid, dilute acid, and heat, then treat or work up neutralization of the reaction mixture, we get amino acid. The mechanism of this reaction started by amination of carbonyl group to form imine. And the amine gets proton from ammonium chloride to be iminium form activating form. The cyanide will attack on the carbon of the iminium form to form the alpha aminonitrile, which upon hydrolysis of the cyanide will lead to the formation of amino acids. Alpha amino acids can be prepared by reductive amination of alpha keto acid. Alpha keto acid, upon reaction with ammonia in presence of reducing agent like sodium cyanoborohydride, leads to the formation of amino acid, of course, after the following up neutralization of the medium. Method 3, alkylation of aminomalonate derivatives. Malonic acid, when treated with sodium nitrite in aqueous acetic acid, gives the oxime, which upon reduction with hydrogen palladium on carbon, the oxime dysfunction group will turn up to amino. Protect the NH via acylation reaction using acetyl chloride pyridine, give N-acyl. We can obtain the same compound in one step by reacting the oxime with zinc acetic acid as a reducing agent and acetic anhydride as a acylating agent to form alpha acetamidomalonate. Okay? Now, taking this molecule, remember this is alpha carbon, okay, to the carbonyl. So it's highly acidic. So when we treat this molecule with sodium ethoxide, we form the anion. You can now insert any R group. Here we have benzyl chloride, so we'll end up by adding the benzyl group. Now, when you add water, HCl, and heat, you hydrolyze the ester to carboxylic acid. And because that is beta carbonyl, or upon heat, you will lose CO2. And also you have here an amide, which can be hydrolyzed easily under this condition. So we will end up with amino acid. Method 4, they call it Gabriel Malonic ester synthesis. We start with potassium phthalimide reacted with bromo alpha bromo malonate. We get these species. When treat this with sodium ethoxide in ethanol, you get the anion. You reacted with Rx, whatever you want. Okay, so R here will get into here. Okay, substitution reaction. Then hydrolyze with acidified water and heat. You get the amino acid. If you do it without the addition of ethoxide followed by Rx, we get the glycine. Show how you would synthesize phenylalanine from 3-phenylpropanoic acid. That's 3-phenylpropanoic acid. 1, 2, 3, and here you have phenyl. And you would like to get alanine, and that's phenylalanine. That's the structure. Well, the first step we will do Helvald-Zelensky reaction using bromine phosphorus tribromide followed by water. You get alpha bromocarboxylic acid. You react that with large excess ammonia followed by neutralization to get the phenylalanine. Well, if we started with potassium phthalimide reacted with bromo diethyl bromomalonate, you get this species again. As we mentioned, here is acidic hydrogen. Sodium ethoxide ethanol will form with the anion, followed by reaction with benzyl bromide, nucleophilic substitution reaction to form the benzyl in here. Hydrolysis with water, acidified water and heat provides phenylalanine. Resolution of amino acids. All the above mentioned syntheses produce racemic products. In most cases, only the L enantiomers are biologically active. The D enantiomer may even be toxic. So we have to really separate them, and we have the L enantiomer in hand to be able to synthesize peptide. So we have method A. By reacting the racemic amino acids with chiral, optically pure chiral acid or base to form 2-distereoisomeric salt that really they are different in physical properties, that we can separate them by either chromatography or just crystallization. We have mentioned that in detail in Organic 1. Here we have pure example of naturally occurring pure chiral base, 2 examples, and tartaric acid as optically pure chiral acid. We can also use enzymes. Enzymes are chiral molecules with specific catalytic activities. When an acylated amino acid is treated with an enzyme like HOG kidney acylase or carboxypeptidase, the enzyme cleaves the acyl group from just the molecules having the natural L configuration. So we have here mixture of D and L. We acylate them, so we have N-acyl, N-acyl. Then we apply enzyme acylase. The acylase will deprotect the naturally occurring L isomer, and we get the L deprotected amino acid, and will not recognize the D isomer. So we have here mixture of deacylated and acylated L and D, which can be separated easily by chromatography again or crystallization. See you next lecture.